Welcome, omgelekile, welcome, and how's it to all you curious, nerdy minds? Whether it's hot, cold, day or night, I'm really honored to be in your company and have your time and attention. If by any chance you are here unintentionally, you can click skip ad in the bottom right hand corner. Just kidding. So, I take it you want to know what makes the Earth the right temperature. Well, good news, you have come to the right place. In order for us to figure out what makes the Earth not too hot, not too cold, we first need to build a climate model, which is based on the atmosphere. Then we will compare the findings to other planets that are closest to Earth and work from the assumption of how things seem at first glance, and then explain why that isn't so. So, to break this down, we'll test the hypothesis. Is it the right distance from the Sun that makes the Earth the right temperature? And to do this, we'll need to build a simple model which would be based on radiation law, self-advancement law, the conservation of energy, albedo, and then we'll explore alternative explanations and conclude. To orientate ourselves in terms of where we are, we need to first go and look at the Milky Way galaxy. The Milky Way galaxy was first described by Aristotle. It is part of the local cluster, even though there are 200 billion galaxies, and it has the solar system which orbits its center. A reminder of some high school geography. The solar system is basically everything that is centered around the Sun. Since the Sun has 99.85% of the mass of the solar system, it has a very high gravitational pull on all the other planets. The inner four planets are known as terrestrial planets because their surfaces are compact and rocky, whereas the outer planets are called gaseous, or Jupiter-like, or Jovian if you want to be fancy. But of all the planets that we know of, Earth is the only one that has water. Hashtag water is life. Let's look at the Sun, which is the primary source of energy and the star of the show. The core is the innermost 10% of the Sun's mass. It is where the energy from nuclear fusion is generated. But because of the enormous amount of gravity compression from all the layers above it, the core is very hot and dense. Nuclear fusion requires extremely high temperatures and densities, and the Sun's interior is still gaseous all the way to the core because of the extreme temperatures. There's no molten rock like we find in the interior of the Earth. The radiator zone is where the energy is transported from the super hot interior to the colder outer layers by photons. Technically, this also includes the core. The radiative zone includes the inner approximately 85% of the Sun's radius, and the energy in the 15% of the Sun's radius is transported by bulk motions of gas in a process called convection. Pardon me. And so now we know about our galaxy, which is the Milky Way, the solar system, which is everything that centers around the Sun. Let's consider other factors that determine the temperature of the Earth. So, is the Earth the Earth habitable temperature because it's the right distance from the Sun? So basically, as scientists, what we'll do then is compare those two factors, put them against each other. So when we put surface temperature versus distance from the Sun, at first glance, it seems to support our hypothesis that the Earth is a habitable temperature because of the distance that it is from the Sun. Because the closer you are to the Sun, the higher your temperature, and vice versa. But as scientists, we always want to test the hypothesis because that's just in our nature. It's who we are. So let's create a simple model to investigate this concept by calculating the temperature if the planets were balls of rock of a given color and distance from the Sun. So this means they have no atmosphere or oceans, which would enable us to compare apples and apples, pawpaws and pawpaws, or however you may have it. But to build a realistic model, we first need to know how the Earth receives energy from the Sun. And the simple answer is radiation. Radiation is transfer of energy from the Sun by electromagnetic waves in a vacuum. So it varies spatially and temporally, and it comes in short wave or long wave, and interacts with different gases in the atmosphere. It moves in the speed of light and it spreads in all directions and in straight lines. But it's dealt with more in depth in the next talk, so we'll just give you some basics for now. But since photons, or packets of electromagnetic radiation that carry information, all travel at the speed of light in a vacuum, we can use this equation to describe that relationship because each photon has direction, frequency, wavelength, and polarization. The funny looking sign at the top, which stands for wavelength, is lambda, which is the 11th letter of the Greek alphabet, and what looks like a V is actually nu, which is the 13th letter of the Greek alphabet. So only three things can happen when radiation of wavelength lambda hits an object or substance. Part or all can be reflected, which is characterized by reflectivity, transmitted, which is characterized by transmissivity, or absorbed, which is characterized by absorptivity, as you guessed. So, but the absorptivity is what actually raises the temperature of the object. So all objects emit radiation as a function of the temperature. So when radiation is absorbed by the objects, it increases molecular motion, which increases temperature. But a black body, which is an idealization because no object that exists exhibits those properties. A black body absorbs all radiation incident on it, and it has an ideal emission efficiency. So emissivity is equal to 1, and an object with less than 1 is a gray body, which is a non-ideal emission efficiency. So how do we measure the total energy, that is, the total energy emitted? Sorry? I can't hear you. Just kidding. The simple answer is the Stefan-Boltzmann law. So basically, this law, what this law translates to is that the total energy emitted is a function of the emissivity and the temperature of the emitting object. Therefore, as more energy is absorbed and its temperature increases, it increases the rate at which the energy is emitted. So then how do we measure the sunlight energy that is reflected? Exactly, albedo. I like you. So albedo defines the percentage of the solar energy reflected back by a surface. So the type of surface determines how it is absorbed, reflected, and radiated. Objects that tend to be white have a high albedo, and those that are black have a low albedo. But the cloud cover also affects the amount one actually reaching the object and the energy that's radiated back. Let's look at this for a simple example. On two ends of the spectrum, you have snow on the one hand, which reflects 70% of the energy received, and dark soil, which only represents 10%. And we all know that dark soil is a darker shade than snow. In our final consideration in the model, let's consider the law of conservation of energy. So energy can either be created or destroyed. Therefore, the sum of all energies in the system must be constant. Therefore, the continual absorption of sunlight would lead to a steady increase in temperature if there's no loss to offset the gain. But every object loses heat to its surroundings at a rate that depends on its temperature. Hence, if the temperature of a planet were to increase because of the absorption of heat from the sun, then the rate at which it radiates the heat will also increase. Finally, in a state of equilibrium, the average temperature of a planet remains constant, and the net incoming solar radiation is equal to the long-wave outgoing radiation at the top of the planet's atmosphere. So, now we know how much the energy the Earth receives from the sun and how much it reflects, and we know that these two should be in balance. Let's work out the effective temperature. And we'll do this by rearranging the Stefan-Boltzmann law, and we'll come to this interpretation which relates the intensity of solar radiation to the surface temperature of the Earth. Okay. So we substitute the variables in red to calculate what this would be for the Earth specifically. So the irradiance flux is the energy received per square meter on Earth from the sun. And when we plug in these variables, we come to the conclusion that the temperature of the Earth would then be minus 18 degrees Celsius if the Earth was a ball of rock with no atmosphere or oceans or anything else, just a ball of rock. So let's see if our model can correctly predict the temperature of the Earth's closest neighbor if they were also balls of rocks. These are the surface temperature results we get if we do the same calculations for the other planets. Obviously, something is wrong with our model because the calculated temperatures are not the same as the observed temperatures. Maybe a graph can show the difference of the two much better. So the empty circles represent the calculated effective temperatures and the filled circles represent the observed temperatures. The dotted lines represent the difference between the calculated and the observed. So according to this, Venus would be colder than Earth even though it's closer, which makes our assumption that distance to the sun alone cannot account for the temperature of the planets. So since our model is wrong, what could be missing? Does size matter? Size of the planet, that is. As you can see, Earth is smaller than Venus but bigger than Mars. So what? Here are the implications of the sizes. So Mercury is the smallest planet and has a negligible atmosphere. Venus has an atmosphere 90 times more dense than that of Earth and is the hottest, even though it's the closest it's closest in relation to the size. And it's got the closest size in relation to the Earth. Earth is large enough to hold a temperature of a particular size. Mars is smaller than Earth and does not have enough gravity to hold any atmosphere. So Venus is too hot, Mars is too cold, but Earth is just right. So basically, it seems that there is something about having an atmosphere that makes planets warmer. Mars is too small to have an atmosphere, so it is too cold. Venus and Earth both have an atmosphere, but the thicker, denser Venusian air keeps the planet far too warm. So the size of the planet, which in turn determines the atmosphere, also has a role to play in determining the temperature. So in conclusion, the hypothesis that the Earth is habitable because it's the right distance from the sun was tested using a simple model. The model assumed the Earth to be a bare ball of rock at the right distance from the sun. The model also required some basic physics, so we looked at albedo, conservation of energy, and the Stefan-Boltzmann law. Using these concepts, we calculated that the Earth's effective temperature would be minus 18 degrees Celsius. Far too cold for life. In fact, using this method, Venus and Mars would also be too cold for life. So in conclusion, the difference between the calculated and the actual temperature was biggest on Venus and smallest on Mars. So what is it that Venus has lots of but Mars very little of? Size. Size matters as it determines the amount of atmosphere. So we suspect that the atmosphere has an effect on the temperature. So our new hypothesis is then the atmosphere of the planet has a bigger effect on the temperature than the distance from the sun does. But how? To find out more, we'll have to investigate a little bit more about light and air. But so far, we can conclude that the distance from the sun, that the size of the atmosphere, which determines the atmosphere, the distance, let me start again. So we can conclude that it's not only the distance, but also the size, which determines the atmosphere, are some of the factors which contribute towards making the Earth not too hot, not too cold, but just right. Thank you for your time and attention. Enjoy the next talk, and please feel free to comment and contribute or whatever else that you'd like to share on this talk. Have a good one. Peace.